Hi everyone, today I'm going to be talking about my paper, FairyWREN, a sustainable cache for write-read-erase interfaces. And so you might be asking me what a FairyWREN is. It's this wonderful Australian bird, which we mostly chose because it has great adjectives like superb, and we really needed a superb project to go with it. So why are we talking about sustainability? Well, if you went to the keynote, you might know a little bit of this, but really data centers are a large emitter. By 2050, they're projected to emit up to 33% of global emissions. And if we start looking within the data center where those emissions are coming from, about 40% is storage. So with this project, what we're looking at is how can we reduce emissions, particularly in storage and particularly in caching on flash. So with FairyWREN, we're trying to enable sustainable caching. What does that mean? Well, it means two things. We need to be able to use longer lifetimes and denser flash, but we need to be able to do this without relying on too much DRAM. And so in order to do this, we need to start with a DRAM overhead solution, low DRAM overhead solution, and get rid of writes. And so in order to get rid of writes, we really need to be able to control all writes in the caching layer. To do this, we introduce a new classification of interfaces called write-read-erase interfaces that allow us to control all writes and then build a cache on top of this that we call FairyWREN, which has several new optimizations to lower writes, which allow us to reduce writes by about 12.5x over prior flash caches, and which leads to a 33% reduction in flash emissions. All right, so the first thing to know when we want to reduce emissions is where are those emissions coming from? For flash caches, they're mostly embodied. And so there's basically two parts of emissions. There's operational emissions and embodied emissions. Operational emissions are coming from energy generation primarily, whereas embodied emissions are coming from things like mining raw materials and building out your flash devices. And the embodied emissions are projected to be about 82% of emissions. And about 61% of data center emissions today are coming from storage. So we need to lower storage emissions. And in this presentation, like I said, I'm going to focus on flash caching. So for flash caching, one of the first constraints is we need a low DRAM overhead. And why would we need a low DRAM overhead? Well, if we look at DRAM versus SSDs, DRAM embodies about 12x more embodied emissions per bit than flash. And DRAM overheads stack up quickly in caching. If we want to index everything in a 2 terabyte flash cache and we take the best index that we see in literature, we end up with about 75 gigabytes of memory overhead, which ends up just being really high in emissions and really a non-starter. So we need, for sustainable flash caching, we need to have a low DRAM overhead solution. The other thing we really need for sustainable caching is we need low writes. And this is because flash has a limited write endurance. We can only write to it so many times before the flash device wears out. In caching, the much easier way to think about this is that we need to have some write rate over time. And so we can get the write rate from our write endurance by taking the capacity, dividing by the desired lifetime, and multiplying by the write endurance. So a concrete example of this is we might want a 2 terabyte flash cache to last for 3 years and have a write endurance from our cells at 3,000 writes per cell. Our write rate that we need to average out over the lifetime of our cache then is 63 megabytes per second. Unfortunately, this is the highest number you'll see today because basically all strategies to lower emissions from our flash cache will also lower our write rate. And so there's two main ways we can lower emissions in the flash device itself. We can use our flash devices for a longer time, a longer lifetime, which basically amortizes our embodied emissions since they're from one-time life cycle events. We can extend lifetime, which amortizes our embodied emissions over more years, right? If we had a 3-year lifetime, we still have the same embodied emissions as if we had a 9-year lifetime. But remember, we care about write rate for our cache, and what this does for our cache is it's going to lower our write rate. If we had 63 megabytes per second at 3 years, we now have 21 megabytes per second at 9 years. Unfortunately, this isn't the only thing that's going to constrain our write rate. We also want to use denser flash. Basically, as we pack more bits into the same hardware, we lower our embodied emissions again. But as we go to denser flash, as we pack more and more bits into the same flash, what we do is we also lower our writes. And so today, if you had a TLC flash device, which is what the numbers you saw before, you could go future to QLC and PLC, and you're lowering the writes quite considerably. And unfortunately, if we look at today's flash caches, don't rely on too much memory like Kangaroo, this is just too few writes with both the lifetime and the density constraint. So for a sustainable flash cache, we need it to have a low DRAM overhead, and we need to have low writes. And really the problem here is writes. We can have a low DRAM overhead cache, But what that ends up doing to us is ending up in a situation where we need to do a lot of random writes, because we've lowered our DRAM overhead by ending up doing a lot of hashing, which creates random writes. And on today's devices, which we're calling Logical Block-Addressable Devices in our paper, or LBAD, what this means is we end up with random writes that then need to go to flash, and we don't have a 4 kilobyte read-write granularity in practice on flash. We rather have to group those into erase units that have to be erased all at once. So we eventually end up in the situation where we have to do garbage collection, right? We end up with a whole bunch of holes as things are getting overridden at the 4 kilobyte granularity, and we eventually have to reclaim space. And so garbage collection will reclaim space, but it'll also incur extra writes, right? And even in the worst case, right, what then comes through, and the cache is like, hey, I want to write something again. And in the worst case, it's something that we just rewrote for garbage collection, right? And so we're forced to do these multiple rewrites, even though it's just garbage collections. We have 2 separate writes. And unfortunately today, right, this garbage collection is happening within the flash device. So there's no control over it from the cache. The cache doesn't necessarily know anything about it. So this interface, the set of interfaces, LBAD, doesn't allow the cache to control all of the writes. But there's an opportunity here if the cache can control all of the writes, right? Garbage collection is an opportunity to do free cache logic. And this is kind of playing off the fact that we're a cache and not a store, because we don't need to keep everything around, right? We need to evict things. So as we move things, as we move data around, we might as well evict from our cache, right? Because we have multiple objects in each of those rewrites. So we need to expose this garbage collection up into the caching level. And there's multiple interfaces we can use to do this, but what we wanted to know in this work is what do we really need from an interface in order to get control over this garbage collection. And so for that, we introduce a classification of interfaces that we call write-read-erase interfaces, or WREN. And so WREN basically exposes this erase unit construct up into the logical layer. And so your cache itself can do sequential writes to an erase unit, and then once it's like, I'm done with all of that data in that erase unit, it can erase that erase unit and reclaim the space. And so there's several WREN type interfaces out there, such as you might have heard of ZNS and FTP. And basically these allow the caches to control all of the writes. But importantly, they don't really get rid of writes. They just move writes to a different part of the stack. So we need something to remove the writes, and that's where FairyWREN comes in. FairyWREN is the cache that leverages the control over erases and writes to reduce writes in the cache. And today, FairyWREN has a lot of components you might see here. I wouldn't spend a ton of time looking at all of them. You can find out more about in the paper, but what I'm going to be focusing on today is a small object cache, which is for objects about 100 to 200 bytes, and this is where most of our writes are coming from. This is based off of Kangaroo, and basically what's happening is we buffer a whole bunch of objects in the log in order to find objects that we can write at once together to a set in our set associative cache, which you might also think of as like a hash table on flash. And the main thing here to note is that there's movement of data, right? We have a bunch of data in the log, and our caching logic is going to move it to the sets. And what we can do is combine this movement, combine this cache eviction and admission policies with the garbage collection that was previously happening in the device. And we call this operation in FairyWREN nest packing, to stay on theme. And so basically we have this garbage collection and this cache logic operations, right? And we can do them together. We can read from our set. We can read a set in either because it's going to be garbage collection, or due to the cache logic, we needing that set, so we read in that set for the caching logic. And from there, we basically do the same operation. We take any new items we need from the caching level and write it to the set, and then we keep doing that loop until we can erase and reclaim space. But what you'll notice is we're basically moving forward on caching logic and garbage collection together so that we can reduce writes. And nest packing is able to reduce writes by about 3.7x. Now, I'm not going to have a ton of time to talk about some of the other write optimizations we do in Kangaroo, or in FairyWREN, sorry, my bad. But we're also able to get write improvements from large and small object separation, so we're able to physically separate different parts of our cache. And then within the small object cache, within those sets, we're able to separate out hot objects that the cache things are hot, right? So they're getting accessed a lot from cold objects that the cache things aren't getting accessed a lot, which creates different lifetimes of our data that we can take into the storage notion of hot and cold and separate out those different lifetimes, and which gets us another 3.4x reduction in in writes. And then finally, we do a lot to make sure our DRAM overhead stays low. And I won't talk about it a bunch, but we get about 8.3 bits per object memory overhead in our small object cache. And so overall, what results do we get? Well, FairyWREN is able to significantly reduce writes. On the y-axis here, you see write rate, and on the x-axis, you see days. So lower is better, right? And we compare FairyWREN to Kangaroo. FairyWREN is able to, on average, get a 12.5x write reduction. And remember, we don't really care about the spikes in terms of sustainability. What we care about is the long-run average of write rate. You could potentially do other engineering optimizations to reduce the spikes. So we're able to get a 12.5x reduction in writes. But what does this mean if we go back to emissions, right? Well, we can take these different caching parameters and we can simulate what their emissions would be using the ACT model. And so here we're going to keep our miss ratio the same on a Twitter trace and aim for a 6-year lifetime and see what our emissions are from different caches. And here emissions is both operational and embodied emissions. So kind of what could we do optimally is this minimum writes line. Basically, you have your emissions from CPU, but you have no extra writes in the system and no extra DRAM. And so you can see you can use PLC, the densest flash we looked at, and that's about half of the emissions. You can see that we're plotting both embodied and operational emissions on the graph. All right, well, what if we had a solution that has really low writes but a lot of DRAM, even if it's highly DRAM optimized? Well, for this, we look at flash yield, and we assume optimistically that there's no extra writes in the system, but unfortunately, it still has too much DRAM, right? So it has the same flash emissions as that optimal case, but its DRAM emissions just make it kind of a non-starter in terms of reducing emissions. Kangaroo, prior flash cache, does the opposite. It basically optimizes for writes and not for DRAM, and you can see it has much lower emissions, but it still has too many writes to be sustainable. The best flash density it can use is TLC, which is, again, too many emissions. So by FairyWREN reducing writes by 12.5x, we're able to use denser flash. In this case, we're able to use QLC, and without so much over-provisioning compared to Kangaroo, allowing us to reduce emissions. So by leveraging new interfaces to reduce writes, we're able to reduce flash emissions by 33%. So just to summarize, FairyWREN enables more sustainable caching, and it does this by making sure it balances the two main constraints that we need in order to create a more carbon-efficient flash cache. By able to use longer lifetime and denser flash on one hand without using too much DRAM. And it does this by leveraging write-read-erase interfaces, which allow us to control the writes in the caching layer. And then we create a flash cache FairyWREN, which leverages WREN to lower writes by things through optimizations such as nest packing, which allows us to reduce writes by 12.5x over prior flash caches, leading to a 33% reduction in flash emissions. Thanks for listening, and I'm happy to take any questions.